In this series of videos, I'm designing and building a Z80 based computer system, and I'm trying to build it in a way that it would have been built back in the day when the Z80 first came out. So it's meant to be a vintage design. As much as possible, I'm sticking to discrete logic for each of the circuits, and I'm trying to avoid large-scale integration devices that came along later. So thanks to anyone that commented. But yes, I know that I could replace the CRT controller with a single device. I could replace this circuit with a single IC, and I have done that many times in the past in other designs, but I'm trying to avoid the use of large-scale devices and stick to the discrete logic design. And I'm writing a book as part of this project, and that will detail each of the circuits, describe exactly how they work, give all the schematics. So there's only so much I can present in the video, but like I said, the stated goal for this project is to stick to discrete design as much as possible. So thanks to everyone that's commented. One of the comments related to this circuit. Now this is the interface I showed in the previous video. This is for the PS2 keyboard interface. We plug a PS2 keyboard into it, and it takes the serial data stream from the PS2 keyboard and turns it into a form that the Z80 can read directly, but it does not require the Z80 to do all the bit bashing to look at each individual bit as it comes in from the keyboard. It only informs the Z80 of the keystroke when the entire keystroke data byte is available, and that takes the burden off the Z80. So in the previous video I said that that would remove the need to have a program or part of the code that bit bashes data in from the keyboard. So if you're using something like a microcontroller, you might well use a bit bashing technique. You connect the clock and the data to a couple of the pins on the microcontroller and look at each data bit as it comes in, and then process the data when the entire byte's available. But what I said in the previous video was we'll put that bit bashing part of the requirement into some discrete logic, which is what this circuit is, and it will remove the need for us to code that. And I received a comment saying I did realise that the code in the ROM is also software. Yes, I realise that, but it's that specific code I'm talking about reducing. It's very rare that you would have the need to look at the data stream from the keyboard in a user application. I'm talking here about the system ROM and reducing the requirement for code in the system ROM, not the user application. And the reason it would reduce that, and the reason I want to reduce that, is hopefully if someone decides to build copies and versions of this machine, they might want to write their own operating system that resides in the ROM. And something like a bit bashing algorithm is fairly complex to code because of the timing constraints that it has to deal with, and it generates multiple interrupts that all have to occur fairly rapidly to read in the data stream. Whereas a design like this only generates one interrupt when the entire data byte is available, and so it greatly simplifies the overall design of the operating system. And that's what I was getting at, that it's going to completely remove the need to do the bit bashing part of the interpretation of the incoming PS2 data stream, and it will just tell the Z80 when the keystroke byte is ready, and that makes it very easy to write the interrupt handler to deal with this. So on to the main topic for today's video, which is the actual interrupt system for our computer. So we've got this interface now which is ready. This will take the data coming from the PS2 data stream without the need for any additional code. It will then try to generate an interrupt, but we need now a facility within our design to allow the Z80 to respond to the interrupt. So we've now got a new circuit to look at. Again, it's a very simple circuit, and this is our interrupt controller. And again, the LEDs are just so I can demonstrate this, but we're going to use mode 2 interrupts in our system, and again I think that may have caused a bit of confusion when I said that in the previous video, and someone said that they had an interface for PS2 Mode 2. I'm not talking about the Mode 2 character set for the PS2, although we will be using that because it is the default set and it's the one that's most appropriate for our application. I'm talking here about the Z80 Mode 2 interrupt. So if you're familiar with the Z80, you know it supports 3 different interrupt modes. If you're not familiar with the Z80, it supports 3 different interrupt modes. So we've got Mode 0, which is really backward compatible with the previous processor, and then we have Mode 1, which is a single vector interrupt, so it will jump to a particular address, and then you'll have a handler at that address, and you have to then figure out which device has generated the interrupt. Usually you would do that by polling the various devices and see which one confesses to generating the interrupt. Mode 2, which is the one that we're going to use, is a much more complex mode, but it's very flexible, and debatably it's maybe beyond what our system needs, but because it's quite easy to implement and gives us so much flexibility and removes a lot of the overhead from the code, it requires more code to initially set it up, but once it's set up, then the overhead for the Z80 is actually quite minimal. So we have our interrupt handling circuit designed. Before I explain how this works, we'll take a brief look at an example Z80 Mode 2 interrupt vector table, and I'll very briefly explain how the Z80 responds to Mode 2 interrupts. So these are just made up values, but it will allow me to explain the basic mechanism the Z80 uses for this type of interrupt. So the first thing we need to do is to create a vector table. These at the moment are made up values. These will most likely, almost certainly, change when we start writing our code. But the point here is that this table is really a series of 16-bit addresses. So these are the addresses of the interrupt handlers on the right here, and this is the address for each byte within the vector table itself. So the vector table starts at address E000 and it ends at E00F. So 16 bytes, 2 bytes for each address. That's how many bytes we need, of course, to store a 16-bit value in the Z80. And so the Z80 can find this table, we need to load the I register when the code starts up with a value of E0, and that's the most significant byte value for the table. So the Z80 then needs to be able to select which of these addresses it's going to branch to when an interrupt occurs. So the way it goes about that is quite interesting. It's very straightforward, but it's quite interesting in the way that it does it. And so if we take interrupt priority 3 as an example, so when the device 3 wants to generate an interrupt, bear in mind that for device 3 we've put the handler for it at this address, A002. We need some way to get the Z80 to branch to this address when that interrupt is thrown. So what happens is this device will generate or try to generate an interrupt by pulling the interrupt line low on the Z80, and it's connected in our case to the maskable interrupt, the INT interrupt line. So the Z80 will continue to execute the current instruction it's processing until it finishes that instruction, and at the end of that instruction it will check to make sure nothing else more urgent is pending. So for example, the non-maskable interrupt takes precedent over the maskable interrupt. But assuming nothing else is pending, then the Z80 will give permission to the interrupting device to continue. The device then needs to place its device vector onto the Z80 data bus. In this case that will be a value of 6. The Z80 then combines the value it's just been given on its data bus with the value in the I register, and in this case that will give us a combined value of E006, and that will cause us to end up at this address. Now this is not the vector for the handler, this is just the address within the vector table. And what the Z80 will do is it will use this address, so it's 2 bytes at E006 and E007, and it will use the value it finds at these two addresses, and it will load that value, in this case A002, into its program counter. Before it does that, it pushes the current program counter onto the stack, so it knows where to jump back to when the handler's finished. That's also why you need the stack to be set up before you can use mode 2 interrupts. And loading this value into the program counter will of course cause the Z80 to branch to this address, and then the interrupt handler will start to run. So the Z80 will then continue to execute instructions from this starting address in the way it would at any other address, and it will continue doing that until it gets to a return from interrupt instruction, at which point it will pop the value for the program counter from the stack into the program counter, and that will cause the Z80 to resume program execution from the address immediately following the one that it was processing when the interrupt was thrown. So it's quite a clever mechanism. It allows us to look up a value in the vector table, does that automatically. All we have to do is make sure our device puts the correct vector onto the data bus when it's told to. So it sounds like a complex set of requirements for the hardware, but as you can see from the circuit, it's very simple and easy for us to do this. So I'll now briefly explain how this circuit works. I'll get it powered up, and then I'll just go through what this does and how it's going to help us with our design in the future. So this is our circuit. The LEDs are just for indication only. This would normally be connected to the Z80 data bus, and we have two inputs. One comes from the in-out, or would come from the in-out request line of the Z80, and the other one is the M1 line from the Z80. The two wires at the top, the yellow and the green, are just two of the interrupt inputs to the circuit. So the green one is our lower priority interrupt, and the yellow is a higher priority. We have 8 in total, of course. So what we have here is very simple. We have a priority encoder, so that's a 74LS148, and it's quite an interesting device. It will allow us to generate a 3-bit binary value, the value of which is the number that relates to the input that's been taken low. So if we take the second input low, for example, the output will show a value of 1. If the next one's taken low, it will show a value of 2, etc. It also generates a low level on another pin anytime any of the inputs are taken low. So that's quite useful to us. It means that anytime any of the inputs go low, we get a low output from that pin, as along with a 3-bit binary value representing which particular pin was taken low. But it does this in a priority fashion, that if there are 2 lines on the inputs that go low at the same time, then the value on the output will be the representation of the highest priority input. So we'll come to this in a few minutes. I'll just go through the sequence. This is then connected to a buffer, tri-state buffer. We need this because the priority encoder does not have tri-state outputs, and also we need 8 bits to feed onto the data bus, not just the 3 bits that we get from the encoder. And so we can set the remaining 5 bits to whatever values we want. Now the bit 0 is always going to be 0 because we need the output from this to go up in 2s, so we can look up the correct values in the table, because of course the addresses in the table go up in increments of 2 because there are 2 bytes for each address. We also have some logic down here to enable us to control the way the circuit operates. And really what this does is it takes the two inputs from the M1 and the in-out request, and it uses those to determine when to enable the buffer. The red LED at the top left is connected to our interrupt output, so whenever the interrupt output line goes low, the red LED will come on, and that's normally connected directly to the interrupt pin of the Z80. So this is currently powered up. What I'll do is generate an interrupt, so the device would normally just pull the interrupt line low, and you can see that the interrupt line going to the Z80 has gone low, so that would trigger the interrupt mechanism within the Z80. But notice nothing has yet appeared on the data bus, because of course this would be the data bus that every other device in the system is using. So what happens next is the Z80 will start this special M1 cycle, so M1 will go low. Notice nothing's happened, but then during that cycle, slightly later on, the in-out request would go low, and when they're both low, the buffer is enabled, and we now get an output fed onto the data bus. So this is the vector that we're using. Bit 0 is at the bottom here, bit 7 is at the top. You notice the top 4 bits I've got all set to 1, and that's by setting the inputs to the buffer to appropriate levels. The bottom bit is set to 0 all the time, and again that's done by setting the input to the buffer to an appropriate level. So the only bits we are really interested in modifying here are bits 1, 2 and 3. In this case, this is input 1 to the device, so we are getting a value here in terms of our 3-bit vector of 1. The yellow jumper, if I just modify this while it's active, is the next interrupt, and so we're now getting the second of the 3 bits set. The reason the top 4 bits are all set to 1 is to make more efficient use of the memory space within the Z80. I'll come back to this in a later video when we start looking at the monitor ROM. But what will happen if we go through the entire sequence the way that the Z80 would handle it? So normally would start in this mode. The data bus would of course be being used by other things, but then a device wants to throw an interrupt, so it would pull the interrupt line low. At the end of the current instruction, the Z80 will see the interrupt line, and assuming everything is well, it will give permission to the device trying to generate the interrupt to continue by starting this special M1 cycle. So the M1 line will go low, then the in-out request line will go low, and that enables the buffer. The Z80 can then read the value from its data bus, and that includes the vector for the device that's throwing the interrupt. It will then combine this value with the value in the I register, and that's what it uses to look up the correct value in the interrupt table. This cycle will end, so the buffer will be disabled again, and then one of the things that the Z80 needs to do in its interrupt handler is carry out whatever actions are required to remove the interrupt. So that will occur sometime during the handler, and then by the time it returns, the interrupt is complete. We get a similar thing if the next interrupt is generated. This is the next priority up, and exactly the same thing will happen. The only difference is, of course, we'll get a different vector on the data bus, allowing the Z80 to select the appropriate handler for this particular interrupt. But what happens if more than one interrupt happens at the same time? So let's say that in this case we get both this priority interrupt and this priority interrupt at the same time. Notice that the interrupt line has gone low again. So the Z80 will respond in exactly the same way. So the M1 cycle will start, the in-out request line will go low, and if you recall, this is the vector for the high priority interrupt, and in fact if I disconnect this one, nothing will change. So in other words, the Z80 will load the vector for the high priority interrupt. It will then finish reading this from the data bus. It will go off and do whatever it needs to with the handler, which should involve or include resetting whatever caused that particular interrupt, and then it will return. But notice that the interrupt LED is still on, so it's dealt with the highest priority interrupt that was active, but now it's got another interrupt it will immediately deal with, and it will do so in the same way. It will generate the special M1 cycle again. In-out request line will go low, but now notice we've got the vector on the data bus for the lower priority interrupt. So the Z80 will then load this, and it will branch to the handler for the low priority interrupt. It will deal with that. The M1 cycle will end. It will jump to the handler, and the handler should clear the interrupt, amongst other things. So in other words, this circuit does everything we need it to for the mode 2 interrupts. We don't need to mess about in software doing this, and this takes a lot of the overhead for our system away from the Z80. It also simplifies the operation and the design of all our ancillary devices, because none of them need to concern themselves with how to put the appropriate vector onto the data bus. That's dealt with for all the interrupts by this circuit. In fact, by this part of the circuit. This, as I said, is just for us to demonstrate this. So just these three devices. In fact, it's just these two devices, because again we already have some of these gates spare on the existing design. So with just two devices, we've enabled the mode 2 hardware design that we need, and removed the need for any of the ancillary circuits to concern themselves with the generation of the vectors. All they have to do is pull a single line low, and then all we need to do to design our system is make sure that those lines are connected to the appropriate input, depending on which priority we want a particular device to have. So this provides everything we need. It has the priority system. This will handle up to 8 interrupts, but you could expand if you want to, and it allows us to connect this directly to the Z80 data bus. We don't need to put any other circuitry in this. It's the entire solution for our hardware side of the mode 2 interrupts. So again, quite simple, quite straightforward, but it gives us a lot of functionality, and it's again surprising what you can do with just a few discrete logic devices. So hope that made sense. It will no doubt make more sense as we start writing the monitor ROM, because obviously that will make a lot of use of this. And the first thing we'll be using this for, of course, is to hook to our keyboard controller. So the output from this, if you recall, has a low output whenever a key is pressed, and all we will be doing is connecting that directly to our interrupt input for whichever priority interrupt we wish the keyboard controller to use. So very nice system, and we'll have 7 other interrupts available for our other devices. We will of course need to write the handlers in code, but in terms of the hardware, this is all that we're going to need.